So good afternoon, and sorry for being an obstacle between the talks and the lunch. And I want to talk today. I'm also another non-cold person, and thank you, Gediminas, for inviting me here. So my talk correlates somewhat with what Odette presented us in the first talk of this section. I'm also speaking about waveguide arrays, and I'm also interested in producing deterministic single photons. So it's in a way two parts in this talk. And we start with this little introduction to the quantum optical part of the story. I must say I'm also a theoretician presenting experimental results, so there will be some theory and some experimental results here. So the main part of the theory is that my quantum matter is the quantum chain of optical modes. So basically, it's the same idea as we have a quantum spin chain, and we had an earlier work where we had spin 1/2 systems coupled in this way, but now I really look at bosonic modes, so just you can think about a chain of optical waveguides. But the very specific thing about it is the way how they see each other. So in difference to the previous works, they do not see each other with just next neighbor coupling. What I have here is the dissipative coupling. So they see each other via reservoir. So basically, they are all coupled pairwise to a common path. And this is the actual system, which is a bit difficult to produce. But what we do instead is basically looking at dissipation into common environment. So the main physical ideas behind this specific coupling is, first of all, something which feels very counterintuitive in the first place is that if you have two modes which dissipate into a common environment, they can get entangled, never having been interacted directly. The other thing is, of course, what we know from a nice bunch of works, that we can use dissipation to create coherence. We can use dissipation to do quantum state engineering, to entangle two atomic ensembles, and so on and so forth. So we actually know for quite a good time that dissipation is not always our enemy. So now, how we are going exactly to use it, to employ it, I just solve the very kind of textbook equation, Lindblad equation. So what I have now, I replace the Lindblad equation would describe this genuine system where I have the pairwise dissipative coupling. And this is, for simplicity, I just decide that the relaxation rates into each reservoir are the same. If we looked into a different situation that doesn't bring you much, so it's really kind of a very nice and straightforward assumption. And now, in order to implement this system, what I do, I replace this reservoir by a third mode. So I have now a very lossy mode in between. So good waveguide, bad waveguide, good waveguide, bad waveguide, and so on. And if I do it correctly, which means if I arrange the linear coupling between these waveguides in a proper way, I can adiabatically eliminate this bad waveguide and essentially have this my Lindblad system. This is just the essence of the theory. And then what I can do, obviously, I can follow a textbook on quantum optics and go over to the equation from the Lindblad equation for density matrices to the Fokker-Planck equation for the P function, and now go to the dynamics of coherent amplitudes. And here we see very nice result for our chain, for our simple system, because if you look at the dynamics of coherent amplitudes, I'm just thinking now about just coherent state excitations in each waveguide. So I see that it behaves like a classical random walk in one dimension. So this opens me a way for trying to simulate different complex systems. For example, one interesting feature of my system is that if I go to the continuous limit of this equation, I have something like heat transport equation. So in a way, my light flows through the system like heat. And depending on which orders I look at, if I look now at creation and annihilation operators in different momenta, so I basically see that I have 1D heat transport equation, 2D heat transport equation, but this is not heat which get transported according to Fourier equation, but light. And this heat-like flow is basically retains coherence. This is unusual situation that I have dissipation, but my coherence is not lost. So I can also play with this thermodynamically. I omit it here for the sake of time, but we can try to define, and we did it, we can try to define effective temperature. You can look at heat conductivity. You can even look at phase transitions, where your phase would be the initial quantum state of your light at the input and the state of your light at the output. And you can show that it looks like a phase transition and so on. This is one part of the story which you can follow. The other part of the story is you can try to look at some interesting stationary states of this system. And here, for example, obviously, if you put in one photon in a chain, you get highly entangled state at the output. Depending, again, on different inputs, you can get Gibbs state with maximum entropy, and so on and so forth. You can get highly correlated states. So there is a lot of kind of playground for a lot of possibilities. But what we are interested in is not just to look at something which you can create on the paper. We're interested in following what you can do really in the lab. And with this respect, we first reverted to very classical, sort of classical situation. We looked at the only classical input. So at the moment, for the moment in the lab, our excitation is coherent states, just laser, right? So the system which we use, how we emulate our Lindblad system, is we'll take the waveguide chain, and so this is what is my actual chain, these gray circles. This is just a waveguide array. But when I want to do a bed waveguide, what I do, I basically take a waveguide and attach a tail of waveguides to it, so that basically an elementary circuit of my system looks like this. This is the actual chain, and this is a tail, which basically is the reservoir, which provides for dissipative coupling. And again, like in the talk of Adet, we replace the time evolution by the space evolution. So now instead of looking at the gamma t in Lindblad equation, I look at the propagation along the waveguide. So my gamma t becomes kappa z, where kappa is the coupling. And now another thing is also, when I really kind of want to study further dynamics, it's very inconvenient to produce lots of samples with different lengths and so on and so forth. And we do a little trick, because it's basically changing the lengths is basically equivalent to changing the wavelengths of the light. So basically, because my coupling constant is dependent on the wavelength of the light, so basically when we look at the dynamics of our system, I kind of prepare one sample like this, which is just a tiny glass plate with laser-inscribed waveguides. And then what I do, I just change the wavelengths of my light and see the dynamics, basically this Lindblad dynamics. This is done in the experimental group, photonic instrumentation group at Heriot-Watt University, who are our experimental collaborators. And this replacement is justified. You can see that the ratio, what is essential for me is the ratio between the coupling constants. It stays enough stable for me to play like this. So, and the first thing which we wanted to see, to make sure we have indeed this common behavior, this common phenomena, collective phenomena induced by the dissipation, is to look at something which we called optical equalizer. So if I look, although I do everything classically, there's actually a quantum effect in the sense that what I do, I take a multi-mode quantum state and symmetrize it over all modes. So if so the output is given like this. So any function of this collective operator of this form is preserved, which means that if I start with input coherent state, what I get at the output, it will not be a statistical mixture of my input states, but it will be a pure state determined by the number of waveguides. So basically I will kind of symmetrize my input coherent state over all of the waveguides. For example, if I have light, which I couple light in each waveguide with random phase and amplitude, at the output light will be completely eliminated. If I have like zero mean random fluctuations, they will be smoothed out and I will get kind of a stable output. So this looks basically like this. If you start with with such type of, depending how you better read it, like here or here, if I start with this random thing, I get at the output an even distribution if I have enough propagation lengths. Or if I start with just one waveguide excited like here, I get again a smoothly distributed coherent light over the waveguides. And this is a slight illumination where I have opposite phases and amplitudes and so on. And this is what we start with to do an experiment to make sure that we get the distributive coupling. And you don't even need to have a long chain. Even with just this elementary circuit, you get the light equalization. You see here we excite initially just one waveguide, and it gets distributed equally between the two waveguides. Or you can do it like with longer chains. We just do, for the start, just 5 waveguides. Again, you see the distribution, the equalization between the different waveguides. And this is the first step to make sure that it works in this quasi-classical regime. And then we're going to move on in more fancy, more quantum stuff. Oh, sorry. I didn't look what I pressed. Yep. There is another interesting thing. If we go now further from just this one simple arrangement, if we go for two-dimensional structures, like for two coupled chains or for lattices and so on and so forth, a whole range of interesting behavior. For example, this is one of such circuits. Again, I first work with just coherent light. Imagine a structure like this. This is now my waveguides, and I just indicate this distributive coupling by blue connections. And here I have a control node and can basically route the light in desired direction. So if I excite both arms, here, both control modes here, light will go up here. If I excite just this one mode, light will go in both directions. If I excite these two modes with opposite phase, the light will go in the lower arm and so on. So it kind of can work as a router. If I do lattice structures, I can reach localization of light and so on, compacton type states and so on and so forth. So it's a very interesting system to play with. And the first ideas in this purely classical realm would be even to applications in some telecommunication standards, where the problem is that due to fiber dispersion, different channels get slight fluctuation and amplitudes and phases, which is actually bad for the signal transfer. So this equalizer can be used. We can try to think how to adapt this equalizer for removing this problem, and so on and so forth. This would be the sort of more telecommunication-oriented part. And now we can also go to this topological photonics. So there's this experimental group we're working with already did a bunch of work together with Erika Andersen and Patrick Öberg and Heriot-Watt University, where they just used the normal coupling, just next neighbor coupling, written big lattices, which is not problem for them, like with 600 elements and so on, to show different types of, to emulate different types of condensed matter behavior. And this is one of the directions we are planning to go. The other direction is what I want to concentrate in the last part of my talk, is to include nonlinearity and to try to use the system as a deterministic quantum source. So let's see what I have in mind. We take now only this elementary circuit, which I showed you in the beginning, just two waveguides coupled to a lossy waveguide, or in other words, like I have these two waveguides and the tail. And I have just a normal laser input. And I want to get at the output as a single photon or kind of strongly subparsonian light. What is the motivation behind here? We all know that a lot of groups are working towards very kind of fancy designed single photon sources with single emitters, which require, where we are aiming at very high, or rather very low G2, and so on and so forth. But despite of having all these great sources, in a lot of experiments, people are quite keen to have something cheap and simple. No? A lot of groups still works with just attenuated coherent light if they want to have quasi-single photons. But in all these experiments, these multi-photon components, which are inevitably there due to Parsonian statistics, are very kind of harmful. So what we are after here is to get something which is really cheap and straightforward. I want to have classical input, just coherent light, and I want to get a quasi single photon as the output deterministically. So how, what I can reach here? So the idea behind it is presented here. So I have two modes, which are single modes. I have here a third mode, which is extremely lossy, which I indicate by attaching a reservoir to it. And these waveguides, they live in nonlinear medium, so I have kernel linearity in the system. And what I can do, due to the engineered nonlinear loss, I can arrange a two-photon absorption mechanism here. And this, for the optical situation, it was first discussed in this paper. For atomic gases, exciton by exciton systems, it was done in the group of Yamamoto theoretically back in '99. So basically, it reduces to these two waveguides seeing each other through dissipative coupling. And if I have here asymmetric coupling, I can reach a single photon at the output, ideally, theoretically. If I have equal coupling, I can get the phase state like the Yamamoto did in his paper for this type of systems. And the mechanism, as I said, is the possibility to have two-photon absorption. Let's look at it in a bit more in a detail. So my Hamiltonian looks like this, because mode 3 can be adiabatically eliminated, again, like in the first part of my talk. And this is in my Lindblad equation, where I now replaced explicitly the time evolution by the Z evolution. And if I now forget for the moment even about nonlinearity, it's very easy then to understand what's going on, because then I have just a dissipative beam splitter Hamiltonian, which means I have two collective modes, symmetric and antisymmetric, one of which is preserved and the other eliminated. So I basically revert to these two modes instead of looking at just initial coherent modes, I have these symmetric modes. And then what I can look at the nonlinear interaction between these two collective modes. And because I have the nonlinear absorption, I can tailor the dissipation, basically nonlinear dissipation. Nonlinear loss can suppress linear loss, and I can arrange for different dissipation channels, two-photon absorption, three-photon absorption, and so on. And then it is possible for antisymmetric mode to behave like shown in this picture. So if I would not have any technical limitations, so irrespective of how much photons you have initially, nearly irrespective of how much photons you have initially in your mode, it will kind of dissipate very quickly to a single photon. And so the limitation is obviously the loss, the need for high nonlinearity and for low loss, right? So what we are expecting, we are not expecting that in realistic system we ever will get to a single photon, but we expect to have very good Poissonian statistic. So what we do is basically we take this our waveguide with tail, gain the same modes, and the asymmetric mode is eliminated, and this basically switches off the single photon loss. Then this mode is enhanced, or rather preserved, and this enforces the two-photon loss. And then, if you look at the we played a little bit with modeling. It's interesting that there are basically two main mechanisms behind it, just the engineered nonlinear absorption, which also survives in semi-classical regime if you look at the mean field theory, and the purely two-photon absorption component, which is only visible if we do the full quantum simulation or quantum analytical solution. And we can see the behavior of the G2 function, and also like this graph is maybe not necessarily to go into too much detail here, but it's just showing how well our approximate system emulates what we want it to be. And it all works nicely, so the summary for this part is that the asymmetric of two nonlinear waveguides to the set absorptive waveguide allows me to have such a behavior in collective mode, which basically means I have a deterministic source of few photon source with sub-Poissonian statistic. Ideally, it could be a single photon if I find a system which has high nonlinearity and low loss. The point is that the two-photon loss is arranged. So, and this leads to rapid narrowing of the photon number distribution, and because the single photon state is not affected by two-photon loss, it becomes a stationary quantum state of the system. So it basically all decays to a single photon. This is, and in terms of applications, it's many applications, as we know, and basically everywhere where I need a kind of to cut off multi-photon components, it can be also quantum computing experiments. It can be, for example, the QKD stuff. So it all kind of it all comes in quite useful. So this is it, and I would like to thank my team working on this and the collaborators, the experimental collaborators at the Heriot-Watt, and the theory collaborator Dmitry Mogilevtsev at Minsk, in Minsk, at the National Academy. And we have postdoc positions available both in theory and in experiment to work on this topic. And I thank you for your attention.